4.3 Lesson 1, Derivative of a Quotient of Two Functions. Objectives. 1. You will know the differentiation rule for finding the derivative of a quotient of two functions. You will understand that the quotient rule is derived from the definition of the derivative as a function, and you'll be able to use the quotient rule to find the derivative of a quotient of two functions. So our vocabulary for today is definition of the derivative as a function, quotient rule, and chain rule. So in this lesson, we'd like to consider a function that is a quotient of two differentiable functions f and g, where the denominator is not equal to 0. The question is, what is the derivative of this function? One might think that the derivative is equal to just the derivative of the numerator divided by the derivative of the function in the denominator. But this is actually not the case. This is not correct. So what is the correct way of finding the derivative of a quotient of two differentiable functions, and why is it that it has to be done in that way? To answer that question, we need to go back to how we defined the derivative as a function. We will take this opportunity to review something that we learned during the fall quarter, and that was, of course, the definition of the derivative of a function. So we're looking at the graph of a function f, and the graph of the function f is a curve in the xy plane. And we have 2 points on the graph of the function f. Let's call them points A and B. So the x-coordinate of point A is x, and the x-coordinate of point B is the x-coordinate of point A plus a small amount represented by delta x. Sometimes we use h, sometimes we use delta x. But the idea is you're adding a small amount to the x-coordinate of point A to get the x-coordinate of point B. The y-coordinate of point A is given by the function f evaluated at the input x, and the y-coordinate of point B is given by the function f evaluated at the input of x plus delta x. What does this difference quotient represent from the definition of the derivative as a function? It represents the slope of the secant line passing through points A and B. And I will show you why that's the case. How do you find the slope of a line? Subtract the y-coordinates and divide by the difference of the x-coordinates. It is change in y divided by change in x to get the slope. So you have f of, so the change in y would be the y-coordinate of point B minus the y-coordinate of point A. Divide that by the x-coordinate of point B minus the x-coordinate of point A. And of course you can simplify the denominator here because you have x minus x, which is 0, leaving you with just delta x in the denominator. So this difference quotient gives the slope of the secant line passing through points A and B. And we learned during the fall term that if you take the limit of this difference quotient as delta x approaches 0, what that means is because delta x is approaching 0, the difference between the x-coordinates of the 2 points A and B is decreasing. In other words, B is getting closer to A. So what happens when you take the limit of this difference quotient as delta x approaches 0? Point B starts to approach point A, and this limit, if it exists, will give us the slope of the tangent line to the graph of f at point A. It'll give us the slope of the tangent line to the graph of f at point A. And this is what we mean by the derivative of the function f. So f prime of x is equal to this limit. And that's what we have here in the definition. So if you want to find the derivative of a function, this is what you have to use, this definition. So let's go ahead and use this definition to find the derivative of a quotient of two differentiable functions of x. So this is the proof of the quotient rule as presented in the Larson Calculus textbook, and let's go ahead and take a look at that. So you will notice that the function that we have is y is equal to the quotient of the two differentiable functions f and g, where g of x is not equal to 0. So to find the derivative of this function, we must use what is meant by the derivative of a function by using this definition. So to begin the proof of the quotient rule, we start with this definition. Our function is f of x divided by g of x. And this definition states that when you're forming the difference quotient, you must, in the numerator, have the difference of the function evaluated at x plus delta x and the function evaluated at x. And in the denominator, you must have delta x. So here we have the function evaluated at x plus delta x. So we have the numerator f evaluated at x plus delta x and the denominator g evaluated at x plus delta x. And then we are subtracting, I'll use a different color here, we are subtracting the function evaluated at x. And then we're dividing all of that by delta x. And again, what is this? This is the difference quotient giving us the slope of a secant line passing through 2 points on the graph of the function. And then we take the limit of this difference quotient as delta x approaches 0. And why do we do this? Because this is what is meant by the definition. This is what is meant by the derivative of a function. So now we do some algebra. The one thing that you do here is you want to combine these two fractions, so you need a common denominator. So you can multiply the first fraction by g of x over g of x, and you can multiply the second fraction by g of x plus delta x over g of x plus delta x. And then you're going to divide what you have in the numerator by delta x, and that would give you what we have here. So what is done next in this proof? A clever step, we're subtracting and adding the same quantity. If you add and subtract the same quantity, the net effect is adding 0, so you're not changing what you have in the previous line. But why do we do this? Because we're looking ahead and we want to be able to manipulate what we have here in such a way that would allow us to use, once again, this definition of the derivative to substitute some portion of our work with the derivative of either f or g. So now, what is done to get there? So we have to do some algebraic manipulation, and what you will do here is you notice that these two terms separated by this minus sign has a common factor of g of x. So you factor that out. And from the first term you're left with f of x plus delta x, and from the second term you're left with f of x. And then you're going to divide that by delta x. And you do something similar over here. These two terms separated by the minus sign has a common factor of f of x. So when you factor that out from the first term, you're left with g of x. And from the second term, you're left with g of x plus delta x. Furthermore, we would actually not just factor out f of x, we'd factor out negative f of x, which has the effect of changing the sign in front of each of these two terms, so that when you factor out negative f of x, you actually will be left with positive g of x plus delta x and negative g of x, giving you what you have here. Why? Because we factored out a negative f of x from each of the two terms here. And then, of course, we divide that by delta x, and that's what we have in this line. And what happened to this particular part of the denominator? Well, you can rewrite all of this as what you have here divided by the quantity that I circled in red. And doing that, this quantity that was circled in red will now be in the denominator. And how do you take the limit of a quotient? You take the limit of the numerator and you take the limit of the denominator. Remember, I'm talking about taking the limit of a quotient, not the derivative of a quotient. So these are some limit laws that we learned again in the fall term. So now that you've done that, what else do we need to do? So now you need to take a look at what you have in the numerator. There's a minus sign here. And you can observe that you're taking the limit of this quantity as delta x goes to 0. So g of x is not delta x. So you can treat that as a constant and factor it out of the limit. Again, that's also a limit rule that we learned in the fall term. And you have the limit as delta x approaches 0 of this difference quotient. And take a look at the definition of the derivative. What we have that we just talked about is exactly this. So that is f prime of x. So that's why you replace this quantity here with f prime of x multiplied by g of x. And then you have the minus sign, and where did that minus sign come from? It came from factoring out a negative f of x at this step of the work. So that's where that minus sign comes from. And then you factored out negative f of x, so that's where that f of x comes from. And then this manipulation that we do here shows us that when you factor out f of x from the limit, because you're taking the limit as delta x approaches 0, so you can factor out f of x, you have this limit. And that matches the definition of the derivative of a function. So this is, in fact, the derivative of the function g. So you write g prime of x there. And then what do we have in the denominator? What we have in the denominator is the limit as delta x goes to 0 of what we have here. And differentiability implies continuity, so that's also something that we know from calculus. And because the function g is assumed to be differentiable, it is also continuous. So what that means is, as delta x approaches 0, g of x plus delta x will approach g of x. So when you take the limit of what we have here as delta x approaches 0, we will basically have the product of g of x times g of x, which gives us g of x squared. And this is what we call the quotient rule. To find the derivative of a quotient of two differentiable functions, here is what you have to do. And I will read this in words. This is the quotient rule. The derivative of a quotient, where you have the function in the numerator is f and the function in the denominator is g, is given by the denominator times the derivative of the numerator. So where is that coming from? The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. all divided by the square of the denominator. This is what we call the quotient rule, and this is the correct way to find the derivative of a quotient of two differentiable functions. So this is the same quotient rule as stated in your textbook. So if you have a quotient of two differentiable functions u and v, and the denominator is not equal to 0, then the derivative of the quotient is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all over the square of the denominator. It's written slightly differently here, but it's the same thing. So here's our first example. We have differentiate, and our function y is equal to a quotient of two differentiable functions. The function in the numerator is f of x is equal to x to the fourth, and the function in the denominator is g of x is equal to sine x. So we will have to use the quotient rule to find the derivative of this function correctly. So we have y prime is equal to the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all over the square of the denominator. So this is how you set up the work for doing the quotient rule. So now we will go ahead and do the differentiation. So you can see here that you have the derivative with respect to x of x to the fourth. You use the power rule and you get 4x cubed. So I'll go ahead and write that first. I write 4x cubed, and then I have to multiply that by sine x, minus, I know the derivative of sine is cosine, so I will have minus x to the fourth times cosine x. All of that is over sine squared x. So we're actually done with the differentiation. To simplify, you can observe that in the numerator we have two terms separated by this minus sign, and you'll see that there is a common factor of x to the third for the two terms. So we can factor out x to the third from each term, and that would give us y prime is equal to x to the third times 4 sine x minus, I will have one factor of x left from x to the fourth when I factor out x to the third. So I have x times cosine x. All of that is over sine squared x, and that is the correct derivative for this problem. I would like to emphasize that this is the correct way to do it by showing you the incorrect way of doing this. Do not do this problem in this way. The wrong way to do this problem. The wrong way. And why is this wrong? Because we're not using the quotient rule. And why do we have to use the quotient rule? You can refer to the proof that we did of the quotient rule, which of course was derived from the definition of the derivative. So this is the wrong way of doing the problem. You cannot say y is equal to x to the fourth over sine x. So to find y prime, it must be the derivative of the numerator, 4x cubed, divided by the derivative of the denominator, cosine x. This is incorrect, and you can see that it is different from the correct answer. This is our second example, and you can see that what you have here is y is equal to a quotient of two differentiable functions, where the function in the numerator is sine cubed x, and the function in the denominator is cosine of 5x. You should also observe that the function in the numerator is a composition of two functions, and the function in the denominator is also a composition of two functions. For that reason, not only will we have to use the quotient rule to find the derivative, but in the process of applying the quotient rule, we will also have to use the chain rule. We begin by setting up the work for the quotient rule. So we will have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the square of the denominator. So now we just go ahead and do the differentiation. So we have cosine of 5x, and let's do it like this. We would like to focus on what we have here first. So to find the derivative of 3 sine to the third power of x, you would have to use the chain rule. The outside function is raising to the third power, and the inside function is sine. So when you take the derivative of the outside function, so you have 3 sine squared x. This is the derivative of the outside function evaluated at the inside function. And then you're going to multiply by the derivative of the inside function. The derivative of sine is cosine. So you have times cosine x. And of course, don't forget this cosine of 5x that we had. So I'm going to write cosine of 5x here. And then I have this minus sign. So I write minus. And again, you can look at what you have to do here. And just to have less to write on our screen here, I'm going to take a look at the derivative of cosine of 5x. So the outside function is cosine, the inside function is 5x. The derivative of the outside function cosine is negative sine. So I have negative sine of 5x, multiply that by the derivative of the inside function 5x with respect to x, which is of course 5. So I have negative 5 times sine of 5x. And of course, I have this minus sign from the quotient rule. So I have minus negative, which gives me plus. Minus negative is plus 5 times sine of 5x. And then, don't forget this sine cubed x. So I have sine cubed x. And all of that is over cosine squared 5x. So that is, in fact, the derivative. And we're done, but maybe we can do some simplification. As far as simplification goes, you observe the numerator of our answer, and you can see that the numerator has 2 terms separated by this plus sign. And you can see that the 2 terms have a common factor of sine squared x. The second term has 3 factors of sine x. The first term has 2 factors of sine x. So we can factor out sine squared x from each term. And when we do that, from the first term, we'd be left with 3 times cosine x times cosine of 5x. And from the second term, we'd be left with 5 times 1 factor of sine x. I can write that first. And then what else am I left with? I'm also left with sine of 5x. So I can write that second. Again, that's a matter of preference. And then all of that is over cosine squared 5x. That's about as much as I can do for simplification, so this is going to be left as my final answer. And what we have here is the derivative of this function. And we found it by using the quotient rule. So today we learned that when you want to find the derivative of a quotient of 2 differentiable functions, you have to use something called the quotient rule. And the reason why that is because according to the definition of the derivative of a function, if you were to apply this definition to a quotient of two differentiable functions, we get the result called the quotient rule. So that's the correct way of finding the derivative of a quotient of two differentiable functions. You need to memorize this rule, and then you need to be able to use it, as we saw in our two examples, to find the derivative of a quotient of two differentiable functions, where the denominator is not equal to 0.